Assalamualaikum warahmatullahi wabarakatuh. Welcome to our project presentation, which is for BEJ30403 for ECAD, Electronic Circuit Analysis and Design. So this is our project presentation. We are from section 1 and group 3. And for this project title, we get it for design a third order band pass filter. And our lecturer is Dr. Jais bin Lias. A very good lecture, and this is our group member. We are comprises of 4 people, which is the first one is Muhammad Ehsan Hisham Samsudin, CE210033. For the second one, which is Frederick Ting Tohni, CE210133. And the third person is Noor Akmal Azwa binti Rosnan, CE210054. And the last one, which is me, Muhammad Arif Hakim bin Azami, BE220124. Without further ado, let's to the next slide. Okay, we're going straight to our introduction, which is about third order band pass filters using operational amplifier. So for this presentation, I will show it as op-amps. So straight for which is active filters. This band pass filter is active filters. There are 2 types, which is passive filter and active filters. But for this kind of project, we are going to use active filters, which is active filters that allows a specific range of frequency to pass while attenuating frequency outside that range, which is for the band pass filter from here, and we go up and then we go down, which is we're going to accept the only frequency that we want, which is specific range. Okay, the second one, which is consists of multiple stages with op-amps and passive components like resistors and capacitors. Resistor and capacitor you can see in our circuit design. These filters with their roll-off characteristic and multiple poles are widely used in various applications. Designing them requires a profound understanding of circuit analysis and op-amp behavior, enabling engineers to create specialized filters for audio processing, signal processing, and more. For the third one, which is utilizing op-amps, is crucial in electronic circuit analysis and design. They selectively permit desired frequencies, improving the efficiency and functionality of electronic devices and systems across different applications. Some of it we can see in electronic communication and electrical vehicle. So the objective of this project, which is the first one in our section, Dr. Jais already listed out specific specification for each group. For our group, which is group 3, we are tasked to design the third order band pass filter with the specific frequency, which is for the low cutoff, the starting only for FL equals to 500 Hz, and the high cutoff, which is FH equals to 5 kHz. So the second objective is to construct the filter using the suitable op-amps and resistor and also capacitor. You can see the design in our circuit design. The third one is to test the frequency response of the filters, which is we're going to test it again and again in the laboratory, and we're going to conclude what we're going to achieve to the lab. And for the fourth one, which is to study the difference between the simulation result and actual result of the filter. So from the third one from the lab, we're going to test it until we achieve the most ideal data, and we're going to study the difference between the simulation result and the actual result. So we're going to see if there is any error or something else or problem, and so on. And the next part is hardware. I'm going to pass it to Frederick. That's all for me. Thank you.
Good morning, doctor. My name is Frederick Ting. So now I will continue with the part of the hardware that we use in the experiment. So the first is the oscilloscope, which used to generate a periodic waveform continuously at a specific frequency without the need of an input. And the next is the function generator, which is used to produce the periodic outputs by joining pieces of waveforms together. And the next is DC power supply, which used to convert AC power from a standard outlet into a stable DC power source. So next is the part of the calculation. To design a third order bandpass filter, we used a second order low pass filter, a first order low pass filter, a second order high pass filter, and first order high pass filter, which is cascaded into one circuit. So first, to build a second order low pass filter and first order low pass filter circuits, we need to with a high cutoff frequency of 5 kHz using the following formulas, which is FHC equal to 1 over 2 pi RC, and C will be equals to 1 over 2 pi R FHC. So after we substitute into the value, we will get C equals to 0.468 microfarad. So using the typical capacitor value, let C1 equals to 0.47 microfarad. So the next is to build a second order high pass filter and first order high pass filter circuits with the low cutoff frequency, which is 500 Hz, using the following formula, which is FLC equals to 1 over 2 pi RC, and also the same equation. After we substitute into the value, so we will get the answer C equals to 4.681 microfarad. So using the typical capacitor value, let the C equals to 4.7 microfarad. Okay, so to obtain a mid gain of 9 T, an additional non-inverting amplifier is cascaded at the end of the bandpass filter, since total AV equals to 16. So the formula is AVT total of gain equals to gain times amplitude gain, and AMP equals to A total over AV. So we will get the answer 90 divided by 16. So answer is 5.625. So to obtain this gain, let the RF equals to 2 kilo ohm, and we use the following formula, which is A amplitude equals to 1 over RF over RA. So after we substitute the formula, we will get answer 432.432 ohm. So using the typical resistor value, we suggest let the RA equals to 430 ohm. Okay, so next I will pass it to my next member.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Isa Isham Samsudin, and I will present the simulation part of our project of ECAT. So our project consists of three specs, which is the low cutoff frequency of 500 Hz, the high cutoff frequency of 5000 Hz, and the mid gain of 90 or 40 decibel. So first we set the voltage input and set it to 4 voltage peak to peak and 20,000 Hz frequency, so we can calculate all. So this is our op-amp circuit, which consists of 5 op-amp circuit to make this bandpass filter, including this amplifier to increase the gain up to 90. So we have three things to measure with the voltage input, the voltage bandpass filter, and the voltage output. So this will be put into the frequency response block, and we can maximize to see clearer. So there's three lines here with the DC. The DC one is straight because it doesn't oscillate, so it doesn't have any gain or attenuation, so it's maintained straight. But the voltage output, as we can see, get a shape where it start from attenuation up, become a gain of 39.1 at peak. So this is the peak, which when convert to unitless become 90. So at the breakpoint gain, which is at 36.1 because negative 3, we can see that the frequency become 511. 511 very close to the 500 Hz that we needed in the spec. So let's see the other side. The other side for the 36.1 decibel, which is the breakpoint, we can get that 4.69 thousand Hz, very close to the 5000 Hz, only short of 300 Hz. And this is the voltage bandpass filter. It's a little lower than the voltage output, however it maintains the same frequency for low cut off frequency and the high cut off frequency. The only difference is the gain, so that's why we put the amplifier to increase the gain up to 90 or 39.1 decibel. That's all from me. Thank you.
Hello, my name is Nur Akmazan Rosnan. My MAC number CE210054. Next, for analysis. For this analysis, I will compare for the calculation and simulation result. First, for the mid-gain, we use 90 unit loss. Then we calculate by using this formula 20 log A. So the result we get is 39.08, which are 39 dB. For the simulation, 39.1 dB. Then for the passband, for the calculation, we use the total of mid-gain minus 2 dB, which are 39 dB minus 3 dB. So the result for the calculation is 36 dB. For the simulation, 36.1 dB. Then we use 500 Hz for the low cut-off frequency in the calculation and 5 kHz for the high cut-off frequency for the calculation. For the simulation, 499 Hz for the low cut-off frequency and 4.62 kHz for the high cut-off frequency. For the center frequency, for the calculation, we use this formula, which are square root low cut-off frequency times high cut-off frequency. So the result for the calculation are 1.58 kHz, and for the simulation 1.52 kHz. Then for the bandwidth, for the calculation we use the formula of high cut-off frequency minus low cut-off frequency. So the result for calculation we get 4.5 kHz, and for the simulation 4.1 kHz. Next, for the discussion, at the first term we ran into an issue that we did not accurate the intern output result when utilizing the Proteus software. Then we were able to obtain the ultimate expected output for our assignment after brainstorming with our other group member by advice and reference from our lecturer. For the lab, we also did not achieve the same outcome in the we did in the theory, perhaps as a result of too many wire jumping or a VCC supply that is less than 50 volt. So we decided to drop the 4 VPP input resulting in a good VPP output. And last but not least, for the conclusion, we can conclude that a basic bandpass filter may be created by cascading together a low pass filter and a high pass filter. The design of the filter is determined by the order of the filters that must be designed. We may also evaluate our design by comparing theory, calculation, and simulation outcome in Proteus software. That's all, and thank you.